Hi, I'm Valerie Johnson, and here is my Energy and Science Research and Application Screencast. I picked an article called Exchangeable Batteries for Micro EVs, meaning electric vehicles and renewable energy. And it was, the research was completed by 3 Japanese research scientists from the Okinawa Institute of Science and Technology. So, talking about electrical vehicles, by 2020, there's estimated to be about 20 million electrical vehicles on the road. And that's super important because we need these electric vehicles to help us try to reduce that carbon emissions. But more importantly, by 2030, so just a mere 12 years from now, it's expected to have 100 million electric vehicles on the road. So electric vehicles are imperative to reduce those CO2 carbon dioxide emissions. However, charging the electric vehicles, what method is important? Where are they going to get that electricity to run? It makes absolutely no sense if we are going to try to reduce our carbon footprint if we are using fossil fuels to provide electricity to the electric cars. It's kind of counterintuitive on that part. So we need to come up with a renewable resource, and how are we going to be able to get the cars to be charged? So a typical electric vehicle has a very short battery life. That battery life is about 40 miles, unless you go in the high-end Teslas, however. So that's fine for people that are commuting back and forth from work, assuming that their work has a charging station. Now, but there's so many other vehicles that are used on a daily basis. If you are a police officer, if you are a taxi driver, if you are a patrol, all of these, you're driving so much, you don't have time to sit at a charging port and charge. So these 3 Japanese scientists were trying to contemplate the same thing, and they came up with a question. They said, how are we able to use these renewable resources in order to keep electric public vehicles charged? So then they came up with a solution. And this solution no longer requires the car to be parked in order to charge it. Exchangeable batteries. These batteries can be changed out, and while one set of batteries is being charged, the other set is being used in the car. So these 3 guys came up with what they called an exchangeable battery system. And in this exchangeable battery system, there are 3 parts that make it work. The first part is a charging station, and in this charging station, they have the photovoltaic panels at the top. So they're using that renewable energy, and inside and they call them micro electric vehicles, the MEVs are able to be charged as well as the batteries can, and they call this the swap station. Part 2 are these exchangeable batteries, and these batteries, there's 4 in one set, and they have to be lightweight enough to carry a short distance because humans are going to be switching them in and out. And then the third part is this micro electric vehicle, and so it has to be small enough that it can run on exchangeable batteries. Okay, so in this case, they used a patrol car from the Okinawa Institute of Science and Technology. So they decided they did not have the infrastructure to be able to do the full thing. So they came up with a simulation, and they gathered their data in a specific way. The first thing they did was they had to calculate how much energy is required for these microelectric vehicles in order for them to depend on this photovoltaic generation. They came up with this algorithm. They had 3 exchangeable battery systems. Then they varied the capacity of the photovoltaic generation. They said from 1.2 kilowatts to 8.4 kilowatts. And they did it in 1.2 kilowatt increments for a total of 7 different capacities. And then the last thing that they did is they took solar radiation data from December, being the shortest month of the year, or as in daylight, to represent winter, and then July being one of our longest days of the year and representing summer, so that they can get. So in all, they had 42 different cases that they can use as data. So as I said earlier, that there were 3 exchangeable battery systems. Okay, the first one is exchangeable battery system 0. In this case, these electric vehicle charging stations do not have those exchangeable batteries. These are very similar to our electric charging stations now. So the battery, the charge that they either get it from the solar panels or they get it from the grid. And the only, and when they get that electricity, they get the electricity when the car is parked near the charging station. So if during the daytime, when the security car was probably out on patrol, it's not getting charged at all. So there's wasted power there. Then in exchangeable battery system 1, okay, they have the same charging station, but then there's one set of exchangeable batteries. So while one set is inside the electric vehicle, another set is inside the charging station using that power to charge it up. And then the second one is exchangeable battery system 2, in which that there are 2 sets of these exchangeable batteries, so that one of them can charge, and then the other one will be able to charge, and that way there should always be one that is, and there's a lot less wasted energy. So, and then if worse comes to worse, there is still the charge from the grid if there's a very long period of rain or a long period of cloudiness. All right, so then they set up some parameters. First off, they took actual data from a gas-powered patrol vehicle, and they took the GPS position and velocity, and they got approximately 81.5 kilometers a day, plus or minus 10.9, but this is from gas. Then they use this data to estimate the power consumption, and they max that out at 9 kilowatt hours. Then last, they estimated the power generation from the solar system to be about 2.6 kilowatt hours per square meter each day. So they kind of had some exact numbers that they were able to use to plug in to figure out what that self-sufficiency rate was. How much energy is going to be consumed by that vehicle in relation to how much was generated. So kind of the results. Obviously, you have 3 different things. Okay, we're in December, so we're the shortest days of the month. Obviously, because this one right here is the 2 sets. So obviously, that's going to be able to be more efficient. It's going to have a better self-sustaining rate. And then July, again, you can see that obviously the more packs is better, but you're going to have more sunny days. So here's kind of a graph of December, and right here, this was obviously a period of cloudiness, but there was a pretty good amount of solar activity. So this is the battery in the micro electric vehicle. You can see where it was put in, and then as it drains, fully charged and drains. So in the battery group 3, they have different ones where here's the energy that was, pulled from the photovoltaic. Here's where it's drained, and these right here are where it's pulled from the grid. So the problem with the set 0 is that you're seeing that there is a lot of wasted energy. This surplus energy is energy that's not going to anything, where in your 2 set 1 you have a lot more that is actually conserved. So it's a whole lot better when you have these 2 sets of batteries that one is almost always charging, you could probably say it. So here's all like the surplus energy, and these blue ones are the energy from the grid that is being pulled. So somehow, if we can take this surplus energy and somehow conserve it, we shouldn't need to pull this energy from the grid. So the self-sufficiency rate, the red is from photovoltaic and the blue is from the grid. So again, if there's somehow that we can, not waste as much, that would be better. So the issues that were big with this study was, one of them is the battery exchanges. The batteries have to be small. They have to be able to be carried by humans. They are in fact 11 ish kilograms. So you're going to have to change them out a lot. The more of the state of charge they have, the higher the state of charge percentage, then the more often it's going to have to switch it out. And so if you use all of it, you're going to have to switch it out, obviously. But this kind of does an average of, in the winter, there's about 3 exchanges per day, and then there's 4 in the summer. So that takes up time. That messes up with the efficiency. The second one is the degradation of the small batteries. As we know, batteries, they tend to not hold charge very well, and so the degradation of those. And then the last one is that this was just a simulation. It would be nice if they could actually use this simulation and be able to produce real things from it. So the thing that interested me the most about this article was the fact that we're pushing STEM so much, and I think it is a very tangible subject for students, and I think it's one that I could bring to my class as we're talking about energy conservation and the law of conservation of energy, and that the kids are able to brainstorm and even kind of get interested in pursuing this more in the future. All right, thank you.